guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. First, I'd like to appreciate and welcome our incoming member. So kindly feel free and engage us in the comment section, and also check the description boxes for various videos that we have uploaded. I normally put a link of similar discussions there, so open those links and check the discussions, and also of course they are going to play a complementary role in assisting us understand the overall concepts that are under discussion. So in this case today we're going to look at the concept of Planck's quantum theory, and this is one of the basic principles of quantum mechanics apart from the wave particle duality that we had done in our previous video. Now in this case we are going to see that the contribution of Max Planck is going to be vital in trying to explain other laws which are going to be of course depending on the aspect of quantum mechanics. And this of course is on the concept of other contributions of various scientists like Niels Bohr, Ernest, of course Albert Einstein, and also the other Compton in their various experiments that they of course performed to back up the whole concept of this aspect of quantum mechanics. And also we're going to see that some experimental observations which have been confirmed from the concept of the black body theory are of course in support of this particular aspect of the Planck's quantum theory. Now basically the concept of Planck's quantum theory was advanced in order to explain the spectrum of black body radiation, and we're going to see that Max Planck put up various number of hypotheses or the postulates which are going to assist us understand this specific aspect of the quantum theory that he had advanced. And of course the various hypotheses are going to assist us understand what were basically Max Planck's argument. Now Max Planck proposed that a black body, which basically had spoken about in one of our videos, had given a spectrum. I'm going to put a link on the similar discussion on the description box of this particular video. We had said that a black body is a perfect emitter and a perfect absorber of radiation. So in this case, Max Planck tried to give the explanation of a black body radiation, which of course had given a unique spectrum. And of course this was done in terms of this specific theory that he had advanced, referred to as Planck's quantum theory. Now according to Max Planck, a black body consists of a large number of oscillators which are vibrating at a characteristic frequency. So one of his arguments is that a black body consisted of a large number of oscillators. Now these oscillators, we're going to of course look at them as vibrators, or particles which are going to vibrate, that Max Planck referred to as oscillators. Now Max Planck argued that these oscillators are vibrating at characteristic frequency, which means each oscillator is going to vibrate at its own frequency, which of course he gave, or we're going to give in terms of this specific symbol. Now in his argument he had said that these oscillators are vibrating at characteristic frequency, and as I have mentioned already in this specific illustration of a black body, I've said that this black body is going to absorb radiation, and of course at the same time it's going to emit this specific radiation. So this radiation is going to be in terms of energy, and of course we are going to see how Max Planck described this specific energy of a black body, or an oscillator that is describing in this particular sense, and how this specific radiation incident and the emitted radiations are going to be described. So in this case, he said that these specific oscillators are going to emit radiation in terms of, or energy in terms of this particular radiation. And of course, this particular radiation are going to be carrying the same frequency as the one that was incident. So if I say that this specific radiation is coming with a frequency that is given as that particular symbol for incident, and then we have this particular symbol for VE for emission, and therefore Vi is equivalent to VE for emission. So this is a particular symbol, basically it's not V. We can refer to it as mu, but this incident is equivalent to the emitted one given as such, according to Max Planck's argument. So he further stated that these particular oscillators are not going to emit energy in a continuous manner, but this energy is going to be emitted in discrete units. So this is going to be emitted in discrete units that he referred to as Quanta. And this basically, this specific discrete unit or small discrete packets are referred to as Quanta, which is basically called as photons. So therefore, I'm going to mention the concept of a photon, which basically refers to this packet of energy which is being emitted by this particular oscillator from a black body. Now, he further argued that this particular photon can be described in terms of its frequency of vibration, which I had mentioned, together with what we refer to as a particular constant whose description Planck gave us a Planck's constant. So basically, he argued that the energy of these particular photons can be described in terms of their respective frequency, and of course, what we refer to as Planck's constant given in terms of that h. So we're going to give a numerical value for this specific constant later. But of course, the product of this frequency and Planck's constant is going to describe the energy of this specific photon, which are vibrating at a frequency that we are given in terms of a mu, given as such. And of course, this specific energy, as I said, they're going to be given in terms of discrete units. And of course, he had referred to this one as a quanta, which he later described as photons. Now, this energy can be given a description or a algebraic representation, which we are going to give in terms of E is equals H, given as such. So this is going to describe the energy of a photon given in that specific order. So basically, H represents Planck's constant, and this is the frequency. And we're going to have n representing various ranges of numbers, which are going to be basically starting from 1 onwards, given as such. And this is going to describe the energy of this specific oscillators according to Max Planck. Now, according to Planck's argument that these particular oscillators are going to emit energy in terms of discrete units, of course, this is going to be trying to explain the concept of the black body radiation, whereby the emitted energy is going to the emitted energy is going to be changing in a particular way with respect to temperature. And of course, we're going to see that this is also going to have a relationship with the frequency. Now that we have said this is Planck's constant given as a constant, and therefore the change in frequency is going to be having an effect on this particular energy. So therefore, later we're going to see the variation of temperature with this specific concept of the emitted energy. And of course, based on this specific argument that Max Planck had come up with, of course, he came up with an energy to describe, or an average energy to describe the energy of this specific oscillator. And we're going to give it in terms of an equation as given. Of course, we have written our first argument for this specific description of energy, whereby we have said that we can give an energy of an oscillator using this general formula, according to Max Planck, using that specific product for Max Planck's constant and together with the frequency. Now, based on his argument that we have said, of course, Planck described the energy of an oscillator using this specific description, whereby he said that the average energy of an oscillator can be given in terms of Planck's constant and the frequency. And we're going to have this specific factor that I'm going to describe later, perhaps in another video. But this basically was the concept of description of the average energy of an oscillator according to Max Planck. Now, from this particular argument, then therefore, concerning the energy of an oscillator, he had argued that the black body radiation consists of a number of oscillators, which of course are going to be a large number of atomic oscillators. So therefore, we can be able to compute what we refer to as the number of oscillators per unity volume, and of course at a specific wavelength of this specific radiation. Now I'm going to put that particular wavelength from the range of lambda. I'll say that lambda basically represents a wavelength in our description of waves. So I'm going to have a wavelength range between lambda and d lambda, and try to describe this particular aspect of the number of oscillators. And this is going to be described in terms of 8 pi d lambda all over lambda raised to power 4. And I'm going to give an elaboration of this specific formula, perhaps in a different video. But basically, this is going to represent the number of oscillators per unity volume in a specific wavelength range, which I've given between lambda and d, lambda given as such. Now, from these two specific arguments for the description of our average description of our energy and, of course, the number of oscillators, we can be able to calculate the energy density of radiation at a particular range of a wavelength. Now, let's give the range between lambda and, of course, lambda plus d lambda given as such. So we can describe the energy density of this specific radiation between this difference of wavelength. And of course, this is going to be the product between this average energy and the number of oscillators which I've given on the board. And generally, this is going to be given in terms of A lambda, and then we're going to have D lambda given as such for this description of the number of particles on that specific wavelength range. Therefore, we can have this one as a product of the two, whereby we're going to have E lambda, D lambda given in terms of 8 pi lambda to power 4. So this is going to be the product between this one, and that is going to give us HV over all over A HV over KT minus 1. And this, of course, is going to be times D lambda given as such. So this is going to be the energy density of the radiation between this variation in wavelength. And this is going to describe what we call the number, or rather the product between the average energy of an oscillator and the number of oscillators within this wavelength range. Now, the product of the two, of course, we're going to reduce into a formula that we refer to as Planck's radiation formula, which, of course, I had said forms a basis for a number of laws which we are going to come across, especially in various topics on radiation, like the Wien's law, of course, the Rayleigh-James law, Stefan's law, and Newton's laws of cooling, among others that we're going to come across. So basically, we're going to have this one given in terms of 8. So this is a simplification of this specific formula. We're going to have this specific formula E lambda given in terms of 8 all over lambda to power 4. But this frequency can be given in terms, from a description of a frequency, this can be given in terms of C over lambda. So therefore, we're going to do this substitution and have H C. So this other lambda, which is going to form the denominator at this particular point, we're going to combine it with this one so that lambda becomes 2 power 5. And then we're going to have this other section of the equation given in terms of A HV over KT minus 1. And of course, that is going to form a formula that we refer to as Planck's radiation formula. Now, this formula is going to be widely applicable, as I've mentioned, and of course, we're going to come across it in various ranges of descriptions and laws, which especially deals with the spectral emission, and of course, the other areas of concerning with the black body radiation in that specific respect. Now, I presume that we have understood the various hypotheses that were advanced by Max Planck, and of course the culmination into this specific Planck's radiation law, which we have given in last statement, which I said, of course, finds a wide application in various areas, especially which we are going to deal with the various ranges of radiation under the black body, as I've mentioned. So this is going to be Planck's radiation formula. Of course, we're going to come across it, as I've said. So kindly check our description boxes for various links of other videos which are going to be related to this, and they're going to assist us, of course, to understand overall the concept of quantum mechanics, of course, by going through the various principles that we're going to discuss. So that is it for now, guys. By God bless you. Catch us in our next video.